part 2 of our lecture about atmospheric variables and the forces that are acting on the atmosphere. And lurking behind the scenes of all this kind of discussion about how the atmosphere works is Newton's second law. F equals ma. One of the great cornerstones. Half of science, I swear, must be F equals ma. It's just different ways of talking about how the force acting on an object is equal to the mass of the object times the way the object is accelerating. Where the force is, of course, measured in units of newtons, as it always is. The mass is, of course, in kilograms. And our unit for acceleration is meters per second squared. A meter per second squared can be hard to think about. Think about it this way. A meter per second of velocity gained every second. So meters per second, or meters per second squared. Okay, hopefully you know how to think through the units of acceleration, but whatever. Alright, so that's the way we tend to think about F equals ma. Certainly the way Newton taught it, 400 or 500 years ago. But here's the deal. For our purposes, in terms of analyzing the forces at work in the atmosphere, it usually makes sense to move the mass over to the left-hand side of the equation. And then you become, like, it's a force per unit mass causes the acceleration. So your left-hand side is force per unit mass. How many newtons are there acting on each kilogram of air? And then the result is on the right-hand side, the acceleration. Now this F that makes up on the left-hand side, that force that is acting is actually usually not a single force that's acting on an object. It's usually the sum of all the forces that are acting on the object. So at any given time there can be a number of forces acting on whatever, the rocket that you're moving, the car that you're accelerating, the potato that you're shooting out of the potato gun in Physics 101 lab, whatever. The force that is going to be resulting in the acceleration of the object will actually be the sum of a bunch of forces. Force 1, force 2, force 3, whatever. And we can then divide that up, distribute that or whatever the right word in mathematics are, and then we can write our Newton's second law like this, where like the first force per unit mass acting on the object plus the second force per unit mass acting on the object plus the third force per unit mass acting on the object, blah blah blah, as many forces that are acting result in the right hand side of the equation, the acceleration acting on the object. Now so far I've been lazy. All of the forces that I've been writing up there and the acceleration, strictly speaking, are actually vectors. They have both a direction and a magnitude. Gravity is acting that direction with a certain magnitude. Some other force might be acting, this way with a certain magnitude and so on. So we have to actually work with these as vectors, and therefore they need to have those vector signs on there. Same with like the acceleration. Now remember, acceleration is, we're talking in the scientific sense of the word, as in change of velocity. So, I mean, I don't necessarily mean it's going faster. It could be changing the direction. It could be slowing the object down. Acceleration in the sense of change in velocity with respect to time. Oh, why don't we just go ahead and write it that way? We could make that right-hand side of the equation change in velocity with respect to time. dv dt, if that makes you happier. Kind of depends on whether you had calculus or whether you had the calculus-based physics classes and so on. Might make you happier, might not. Now, forces and acceleration are, it's an important thing to be able to think through what they mean. And I'm going to kind of walk you through a classic example of how you can think about how forces acting on an object can result in an explanation of how its motion is changing. How F divided by m equals a. The net force acting on the object results in an acceleration of the object. I got a little tail dragger biplane sitting there on the runway on my diagram here. When it's just sitting there on the runway not moving, there's two forces acting on the airplane. Gravity is pulling the airplane down, but the runway is pushing up on the aircraft, keeping it from crushing down and going down into the center of the Earth, right? The ground is pushing up. It happens to be a manifestation of the strong nuclear force and all that. Don't worry about that. The point is, when it's sitting there on the runway, there's two forces, and they are equal and opposite. Gravity pushing down, the runway pushing up, the two forces add up to 0. So there's no net force acting on the biplane that's sitting there on the ground. Therefore, it's experiencing no acceleration. Its velocity is not changing. Well, at the moment, it doesn't have any velocity, so its velocity not changing means it stays right there. Alright, now my plane is going to start racing down the runway. Now, when the plane is taking off, at first, as it's going down, it's not flying. The wings are producing lift because air is flowing over the wings. That's what wings do. They produce lift. But apparently the amount of lift it is generating it's not enough to lift the plane yet. But, so the gravity is still pulling the plane down towards the surface of the Earth, but the plane isn't going down through the pavement. The pavement is pushing up. The pavement, the runway's forces, the strong molecular force within the atomic force within the runway, and the lift generated balance the force of gravity. So there is no net vertical acceleration on the plane. The plane is not accelerating up or down. It is neither going up in the air nor crushing down into the Earth. And as a consequence, the vertical acceleration is zero. It isn't moving vertically at all, so its change in velocity is zero, and its velocity is zero in the vertical direction, and it does not go up or down. Now in the horizontal direction, the engines and the propeller are producing thrust that are pushing the plane forward. At the same time, there's drag. Drag could be acting in the sense of friction or aerodynamic drag, or it could be, whatever. At the present time though, when the airplane is trying to take off, the engine is producing more thrust than the airplane is experiencing drag. There is, when you add those two forces in the horizontal direction, there is a net force in the forward direction. Therefore, we are accelerating forward. The velocity of the plane is changing to accelerate it forward, which is what happens on a runway. Alright? How about during ascent? The plane is now taking off and accelerating and going upward. During ascent, there are four forces acting on the airplane. We no longer have to worry about the force of the pavement. It's always hard to think about how objects push back when you push them. But now there's just four forces at work. Gravity, lift, thrust, and drag. Let's focus on the vertical direction first. In the vertical direction, the wings are producing lift. In fact, during takeoff, the plane's wings produce enormous amounts of lift because the pilot makes them. By adjusting the trim on the flaps, the wings can produce more or less lift. The pilot adjusts the flaps so that the wings are producing enormous amounts of lift. More lift than pushing up than gravity pushing down. There is a net force, when you add those two forces, there is a net force up because lift is greater than gravity. So the plane is accelerating upward. Now it starts off not moving very much upward, and therefore is getting faster and faster upward as it is, going in ascent. In the horizontal direction, the plane is continuing to accelerate. If you ever, on an airliner, sometimes they have that nifty GPS system where you can be watching your airspeed and stuff like that. I never watch the movie. I'm always watching the GPS when I'm on an airplane. You can see how the plane is getting faster and faster and faster. Because as the plane is still in ascent, the pilot is really roaring those engines. They're making more thrust than there is aerodynamic drag on the airplane. So in the horizontal direction, there is a net force forward. There is therefore a net acceleration forward. So the velocity in the forward direction gets faster and faster and faster. Okay, that is how ascent works on the plane. Just to kind of complete the analogy here, how about when we're at cruising altitude? Okay, so here's my little biplane cruising along. Now, when the plane is cruising along, the pilot and it's not climbing and it's not descending, the pilot has adjusted the trim on the wings, on the flaps, so that the wings are producing a certain amount of lift. Specifically, they're producing the same amount of lift that exactly balances gravity. When the plane is cruising, you don't want to go up and you don't want to go down. You want to stay at the same altitude. You want no vertical accelerations. So you perfectly balance these two forces so there's no net vertical acceleration, and the plane won't go up and the plane won't go down. Same with way in the horizontal direction. The pilot adjusts the engine so that it is not producing as much thrust anymore, and it produces but they don't turn the engines off either, because they want to produce some thrust so that it exactly balances the aerodynamic drag on the airplane, so that you have drag pointing backwards, slowing the plane down, but you have thrust pushing the plane forward, and as long as they're exactly balanced, then you'll have no horizontal acceleration. The plane's not going to be changing its velocity. It's already got a fast velocity. The plane's already cooking along at whatever its airspeed is, and we don't want that to change. So we no longer have any horizontal acceleration, where we're thinking of acceleration as, the change in velocity. Cool. That's why the plane's engine sounds so much quieter. Like when you're on a jumbo jet or whatever, once you reach cruising altitude, you can hear the pilot, slow down the engines and so on, and they're not producing as much thrust. Because now he wants to go at the same speed that the air traffic controller is telling him to go in, and he doesn't want his velocity to change, and he doesn't want his altitude to change, and he's just cruising. So he only needs to run the engines hard enough to resist to exactly overcome drag. So if those are the kinds of things that are forces at work on, say, an aircraft, well, now we can go back and look at our form of the first law of thermodynamics and start saying, hey, not the first law of thermodynamics, I'm sorry, Newton's second law, and start saying, well, what are the kinds of forces that are at work on air? And your book lists 4, and I added a few others at the bottom there. And let's just kind of pick through this idea of what forces are at work in the Earth's atmosphere. Now, we'll deal with each of them individually, but the first one I want to talk about is the so-called pressure gradient force. Powerful vocabulary word in there, gradient. Gradient is how something changes over a distance. So like how temperature is different from one place to another is a temperature gradient. Or how pressure is different from one place to another is a pressure gradient. There is a pressure gradient between the inside and the outside of this can of spray paint that I have here. And as a consequence, then there is an ability to use that pressure gradient to produce a force that is going to be taking the paint out of, and the gases out of the paint can and put them outside. The pressure gradient force is a force that only exists in places where there is a difference in where pressure is changing over a distance, and it always pushes from areas of higher pressure towards areas of lower pressure. So like I have a weather map down there in this diagram here. We'll zoom in as we need to on places, but those contour lines on there are isobars. They're lines of constant pressure. They help us see that there's an area of high pressure in southern Canada, an area of low pressure in Arkansas, and so on. I've labeled 3 locations there with blue dots. And what I'm going to do is I'm going to figure out what the pressure gradient force is on, or what at least its direction and so on, and its relative magnitude and so on, at different locations on this plot here. So if I were to actually try to draw what I think the vectors of the pressure gradient force look like, you always want your vectors to start at that volume of air that you are analyzing. So like if I'm looking at those 3 blue spots right there, that's where my vector starts. The vectors of the pressure gradient force will always be perpendicular to the contours of pressure in the neighborhood of your parcel of air, your volume of air that you're working on. And the vectors will always point in the direction of the lower pressure. Now, you want your vectors to be drawn to be longer when the contours of pressure are closer together, because the pressure gradient force gets stronger the more pressure is changing. If the pressure is all about the same in that area and pressure isn't changing very much over a distance, there isn't going to be very much of a pressure gradient force. If the pressure is changing a lot over a small area, those isobars, those lines of constant pressure on the map there, will be getting closer and closer together, and you want to make your pressure gradient force vectors longer and longer. Now, there's a whole lot of math to actually talk about the pressure gradient force. If I were going to show you some of the equations that they happen to have in your textbook here, they dwelled for a few moments on the top equation there, where they were saying this P vector, the pressure gradient force vector, P vector, is equal to, well, 1 over rho times del P. That triangle thing there is a del operator, which, depending on what math and physics classes you've had, you may or may not have seen before, but I'm not going to get too dwell on it too much there. As it happens, the del operator can be replaced with the partial derivative of P with respect to x. Oh no, partial derivatives. Again, depending on what calculus classes or what physics classes you've had, that could be a big deal or could not. We're not going to worry about it because we can substitute something in there. We can actually change this and say, what is our pressure gradient force in the x direction, Px, or what is our pressure gradient force in the y direction, Py. Let me show you how we actually do that. I'm going to kind of gray out the map a little bit so we can still see it a little bit, but we're not distracted by the parts we don't need right now. If I wanted to actually compute the pressure gradient force in the x direction, the west to east direction here, I need to know the pressure at some location a little to my east, P east, and the pressure a little bit to my west, P west, and I got to divide by delta x, the distance between those 2 locations. Okay, so like in this case, I'm working with a point that's in southeast Nebraska, and I said, oh, let's say I knew the pressure out over Illinois, and I knew the pressure out in western Nebraska, southwest Nebraska, and if I took the difference between those 2 pressures, I would be getting a sense of the pressure gradient. The pressure gradient being how the pressure is changing over a distance there, and then divided by -1 over rho, multiplied through by -1 over rho, and you get the pressure gradient force in the x direction. And you can see in this case, it's going to be pointing towards the east because there's higher pressure out in like western Nebraska and lower pressure off in like, the Ohio Valley or whatever. Same sort of way, we could do the same sort of thing in the y direction, where we could say, if I wanted to know the pressure gradient force in the north-south direction, I could say, okay, here's my point in southeast Nebraska. If I knew the pressure at some point to the north, P north, and I knew the pressure at some point just to my south, P south, I could take the difference between those two pressures, P north minus P south, and divide by the distance between them, delta y. And we would get the pressure gradient force in the y direction. And in this case, that component of the pressure gradient force, Py, is from the north towards the south, as I've shown in that red vector there, because the pressure is higher to the north and it's lower to the south. So in this case, we have two pressure gradient force components. The x component is pointing off to the east, and the y component is pointing down to the south. And if you did vector addition to add them up, you'd see that the pressure gradient force vector at that location, which I have labeled P, just points from our location, southeast Nebraska, across the perpendicular to the contours of pressure towards areas of low pressure. Okay, so it's not like a huge deal to work it all through. The actual mathematics of it are not the end of the world. It's just algebra. Once you get past the craziness of the del operator and those partial derivatives, you can see that we actually can do this just using basically algebra, right? It's actually just arithmetic, frankly. Atmospheric science majors hear this and they are comfortable with it. And they shouldn't be. Because there's a real fundamental problem with that explanation I just gave you. You should be scratching your head and saying, wait, what? What? If I'm talking about a volume of air that's like sitting there in southeast Nebraska, how does the air that's there even know what the pressure is at these remote locations? How does that air in southeast Nebraska know that the pressure is higher out in western Nebraska? How does it know that the pressure is lower over there in like Illinois? And I'm going to tell you, it doesn't. It doesn't? No, it doesn't. So then wait a minute. How is this pressure gradient force thing really working? I mean, the air only knows about the air around it. This, if we had a 1 cubic meter, 1 meter by 1 meter by 1 meter volume of air sitting in southeast Nebraska, all it knows is the pressure of the air around it. It doesn't know anything about air 500 kilometers to the east and 500 kilometers to the west. Well, let me show you that actually, that's kind of just a little trick. It's a trick to make the math work out. Let's actually work through the math. Alright, so like in this case here, if I'm trying to figure out the px, the pressure gradient force in the x direction here, if I actually look closely at my map there, I can see that the pressure to the west, it's somewhere, that location PW there, it's somewhere between the 1016 and the 1020 millibar contour. Let's say that it's 1018 millibars at that location I have labeled W. That's 101,800 pascals. And that location labeled E, let's say that's right there on the 1004 millibar contour. That looks close enough to me. So that location E has a pressure of about 1004 millibars, or 100,400 pascals. Alright, and the distance between those two is about 1,200 kilometers, which is that very large number of meters. I think that's 1.2 million meters. Would that be right? Yes. Okay. Well, I can just do that math there of P east minus P west divided by delta x, and that works out to 0, oh my goodness, what a tiny number, 0.001167 pascals per meter. That is my pressure gradient. The gradient, how much pressure is changing over a distance, is 0.001167 pascals per meter. Every 1 meter, there's just a teensy little difference in the pressure. So if I took, remember I said I was talking about like a 1 meter by 1 meter by 1 meter block of air down there in southeast Nebraska? Let's actually go take a look at the thing. Here it is. Here's my 1 meter by 1 meter by 1 meter block. And you know what? In the very middle of it, let's say the pressure right there is 1,008 millibars like we read off the map over there. In fact, that's 100,800 pascals, right there at that black dot, right in the middle of that 1 meter by 1 meter by 1 meter box. Where one side of the box is a half meter to the west and the other wall of the box is a half meter to the east. And we could actually plug in our pressure gradient that we learned on that previous slide there, and actually find out what is the pressure, one half of them over on the west side of that box, and what is the pressure on the east side of the box. And those numbers are on there. You can see that the pressure to the west is higher, but such a tiny amount, 100,800.0006 pascals. Whereas pressure over to the east is a little lower. It works out to 100,799.9994 pascals. That is a very, very tiny difference in pressure, way smaller than you could actually measure. But that doesn't mean it's not important to air molecules. And we could take like our ideal gas law, P equals rho RT, and if we make an assumption that the temperature is the same all through this box and so on, we could actually figure out the density of the air on the west side and the east side of the box, and we could from that actually figure out, using Avogadro's law, which we aren't going to learn about right now in the class, we could actually even figure out how many molecules there are on like the west side and the east side of the box. It's called the number density of molecules. And what we would find out is the numbers are huge. There's an enormous number of molecules on the west side of the box, and there's an enormous number of molecules on the east side of the box, but the numbers aren't the same. And even though the difference in the pressure between the east side and the west side of the box is different, there's a lot more molecules on the west side, on the high pressure side of the box, than there is on the east side of the box, where it's lower pressure. The molecules are more crowded over there on the higher pressure side, and they are less crowded over there on the lower pressure side. In fact, the number is quite huge. They're just across that one little box, there are 2.88 times 10 to the 17th more molecules per cubic meter just off to the west of the box than there are off to the east of the box. I had a good time on an Excel spreadsheet figuring out all this math here. So picture, I mean, don't get me wrong, there's a lot of molecules on both sides of the box, but they are more crowded, and not just a little bit more crowded, on the west side, in this case, than on the east side. So of course, these molecules are going to want to diffuse from the place where they are more crowded towards the place where they're less crowded. It doesn't really have anything to do with what the pressure was doing 500 kilometers off to the east in Illinois and 500 kilometers off to the west in western Nebraska. It's really about the tiny little area that we're talking about, that like 1 meter. And we can see how, hey, the molecules are more crowded on one side, they're less crowded on the other. They're going to want, by their own molecular motions, to spread out. They're going to want to go from where they're crowded to where they're less crowded. So when we were using this little way of figuring out the pressure gradient force, where we talked about like we needed to know the pressure at some place off to the east and some pressure off to the west, we use these remote points E and W because that's what we measure. We don't know the pressure every like 1 meter. If we did, we could actually do a better job of figuring out the pressure gradient force and so on. We could actually understand the little microscopic differences in pressure and density and so on that are driving it. But then we don't measure pressure that way. We measure the pressure of weather stations and airports and stuff like that that are, many kilometers apart. So we can use this way of talking about like the pressure a couple hundred miles off to the east and a pressure a couple hundred miles off to the west as a way of getting an estimation to what the pressure gradient force is doing. But the air molecules don't really know or give a damn what the molecules are doing thousands of kilometers away. They just care about the molecules in their area. Oh. Man, that pressure gradient force is strange. Man, atmospheric science majors take way too much on faith. I hope that when you're studying wind, you'll be able to get more of a sense of how it's amazing how these microscopic forces acting on individual little volumes of air produce the wind. Get the idea? I'm a little enthusiastic about this stuff? Yes, I very much am. Hey, let's ask a couple quick questions before we go on to some more horrible forces. Here's question 4. I've got a weather map here with some contours of pressure. You might see there's an area of high pressure centered in like, what is that, Nevada. There's an area of low pressure just north of Minnesota. That's the only features on the map that are most important for this question here. And I got 3 locations labeled A, B, and C. Which of those locations has the strongest pressure gradient force right now? A, B, or C? Take a look at that map, make a choice from those 3 options, and get a little feedback before you move on to question 5.